During the second module, we deal with nuclear physics and its applications. And in this fifth video, we go into more details on the two other types of radioactivity, that is to say, beta and gamma decays. The goals for you are to be able to characterize beta decays of nuclei and their properties, to relate these properties to those of the underlying weak interactions, and to be able to characterize gamma decays of excited nuclei. A neutron-rich nucleus, i.e. one that has n over z larger than what stability requires, can transform into a more stable nucleus by emitting an electron and transforming one of its neutrons into a proton in what is called a beta minus decay. To conserve lepton number, this emission must be accompanied by the emission of an antineutrino. In the contrary case, proton-rich nuclei, which have too many protons to be stable, can reach stability by beta plus decay, accompanied by neutrino emission. Since the proton is lighter than the neutron, this latter process can only happen for a bound proton, where the Q value is turned positive by a gain in binding energy. A nucleus with a surplus of protons can also capture an electron from the internal K shell of the atomic cloud. The other electrons of the atom will then cascade down to fill the gap. Since a lepton disappears in the capture, a neutrino must be emitted to conserve lepton number. All these decays are isobar. They have delta A equal to 0 and delta Z equal to plus or minus 1. Since beta decays are three-body processes, the spectrum of the emitted electron or positron is a continuous one. It has the shape which is sketched in this graph. The neutrino interacts only very weakly with matter. It will normally escape undetected. This is also the reason why the neutrino has taken so long to be discovered. Neutrinos and antineutrinos are fermions with zero electric charge and a very small mass. The maximum electron energy is obtained when the neutrino is produced almost at rest. Its maximum value then approaches the Q value, like it would in a two-body decay. When one measures this energy, one can establish an upper limit on the neutrino mass by energy conservation. The video 2.5a introduces the exponential decay law, which describes the time evolution of this and other decay processes. At the quark level, beta decay proceeds via the exchange of a W boson, which is the gauge boson mediating the weak force, like it is shown in this Feynman graph. The large mass of this boson is responsible for the short range of the weak force and its weakness at low energies. Neutrinos are very peculiar particles. Their generations can mix with each other. Their mass is the lightest among all particles and probably of the order of milli-electron volt. It is not even clear if neutrinos and antineutrinos are really different particles. Their charge is the same, and they have no magnetic dipole moment, contrary to other neutral particles like the neutron, for example. The definitive answer will come from experiments searching for what is called double beta decay. They deal with nuclei where two beta decays happen simultaneously to reach the valley of stability. If neutrino and antineutrino are really the same particle, one of them can then arrange the lepton number of the other one, such that there are no neutrinos emitted in the process at all. If they are not identical, two neutrinos must always be emitted in the process of double beta decay. For a recent review of the experimental situation, please see the article by Rode Johan cited on the bottom of this slide. Weak interactions have two more peculiarities. The first one is that only the left-handed part of the quark and lepton fields participate in the interaction. What we mean by that is that only matter particles with spin anti-parallel to the direction of motion interact via the weak force. The opposite is true for matter antiparticles. Only right-handed antiparticles, which have the spin parallel to the direction of motion, can interact. Neutrinos and down-type quarks, and that is the second peculiarity, which participate in weak interactions are mixtures of the corresponding real particles. One denotes the neutrino mixtures with nu e, nu mu and nu tau according to their generation. They are mixtures of the real particles nu L, nu m and nu h, which we have introduced in the first module. The quark mixtures are denoted by d prime, s prime and b prime for the three generations, mixtures of the real particles d, s and b. We will come back to these astonishing properties in module 6 when we discuss weak interactions in more detail. What I mean by participating in weak interactions is that only the left-handed mixtures are able to emit or absorb weak bosons. What I mean by real particles are quantum eigenstates of the mass operator. These states propagate with a specific velocity when their energy momentum is known. This is not the case for nu e or for the d prime, for example. It is the nu L and the d quark which have a mass which is a constant of motion. Let us now come to the last type of radioactivity, the gamma decays. They often follow another previous decay which leaves the daughter nucleus in an excited state. It can then fall back into its ground state by emitting a photon of a quantized energy. The energy of the photon will correspond to the energy difference between the excited and the ground state. The study of emission and absorption of nuclear gamma rays thus constitutes nuclear spectroscopy, an analogy to atomic spectroscopy. With one remarkable difference, one cannot neglect the recoil of the daughter nucleus in gamma decays. The more massive the system, the less important will be the recoil energy. One can thus freeze the nucleus into a crystal structure which has a much larger mass and allows the recoil to be reduced to almost nothing. This is called the Mössbauer effect. It allows to reduce the line width of gamma decays to of the order of 10 to the minus 7 electron volts, which in turn allows to measure the relative line separation to an accuracy of the order of 10 to the minus 12. One can thus study nuclear energy levels with great precision. This can also be used to measure the composition of materials. We show here an example of the gamma spectrum of natural uranium mineral. It allows to identify and quantify the presence of radionuclides like radium-226, lead-214 and bismuth-214 coming from the decay chain of uranium-238, which itself is not a gamma emitter. In the next video, we are invited to visit the laboratory of the nuclear physics course at University of Geneva to see experiments on radioactivity.